Let's talk about sketching the graph of the original function if we're given the graph of its derivative. So at the top of the page here, I have kind of our basic information that we're using, and it's just the backwards information that we would use if we were given f and asked to sketch its derivative. So we know that anywhere a function is increasing, its derivative will be positive, and anywhere it's decreasing, its derivative will be negative. And that relationship works in both directions. So now we're going to say, well, anywhere the derivative is positive, meaning above the x-axis, like literally positive y value outputs, then the original function would have been increasing. Of course, we mean left to right. And then anytime the derivative is negative, meaning the graph of the derivative is below the x-axis, the original function will be decreasing. And of course, we mean left to right. Okay, let's jump into an example and see how we feel. So here we have the graph of a derivative, and we're asked to sketch the original function. So we're going to do sort of the opposite that we would do if they gave us f and asked for its derivative. So normally, if we start with the original function, we would say, okay, well, where is the derivative 0? I'm going to mark those as x-intercepts on the derivative graph, right? So that would be like tops and bottoms of bumps, which are like local max and min points. So what I'm going to do here is do that backwards, right? So I'm going to look at these 3 x-intercepts on the derivative graph and say, oh, well, those are where f prime is 0, right? It's literally showing a 0 y value. So in the graph of the original function, these will be either the tops or bottoms of bumps. So these are going to be kind of max and min points as we go. Okay, so I also want to break up. So this kind of has my graph in 4 pieces now, right? I've got this chunk, this one, and this one. So for each of these 4, I'm going to put it in one of these 2 categories, and that'll help me kind of put my graph image together. So anywhere the derivative graph is above the x-axis, it's positive numbers. So the original should be increasing. So above the x-axis in this image is this lump right here. And then also this stuff right here. We're above the x-axis. So this would be f increasing because it has a positive number derivative. So between x equals -2 and 0, we're increasing. I have no information about where I should draw this graph. So I'm just going to kind of pick a starting point and say, all right, increasing from -2 to 0. And then I also have the pieces of this graph that are below the x-axis here. These are negative derivative numbers. So all the red stuff here corresponds to where the original graph is decreasing. So between between 0 and +2, this graph should be decreasing. Like that. And then the derivative goes back to increasing here because we have a positive derivative. So it's going to kind of go up. And then I forgot this little bit here, so I'll come back for it. This is a negative derivative, so the graph should be decreasing. Right, so I have roughly a sketch of what I want this picture to look like. Again, it could be this W shape way up in the air, down below. It could be passing through the x-axis here. We actually don't have enough information to pin that down. But what I do definitely want to do before I finalize this answer is smooth this W out so that it doesn't have any corners, right? The way I just sketched it, it kind of has some corners, but I know that if it were a true corner, that would correspond to the derivative not existing, and I don't have any of that here the way that I will in this next example. So I'm going to smooth it out so that I still have a minimum at -2, max at 0, a little minimum low point at +2, and that smoothed out version is my answer. Okay, so a couple things to notice before we move on to the next example. One is that, notice, let's say x equals -2 in this original image here. The derivative went from negative to positive, right, below to above, which means the graph went down and then up. So this is going to give us a little minimum point. Same thing happening at +2. And then at 0, when the derivative went positive to negative, we had a little top of a bump local maximum point here. We can also see a connection to the second derivative here. It's not necessary to make our picture, but we can kind of see some interesting stuff happening. So you might think, well, what are the tops and bottoms of bumps in this image, right? Like we're used to those being really important, and this positive and -1, I didn't really use over here. So if we were doing the graph of this guy's derivative, right, we went the other way. But if we wanted the derivative of this graph, we would be doing the second derivative, so f double prime. So these tops and bottoms of bumps, these are where the second derivative is 0, which corresponds to a change in concavity over here. So 1 and -1 are your changes in concavity. So these are your inflection points in the original graph. So we're concave up, then concave down, then concave up. All right, let's do one more example in this video, just for kind of a weirder one to see. Here we have, again, the graph of a derivative, and we want to sketch the graph of the original function. But this derivative graph has a weird situation in it, right? So we have a jump in the graph at +1. So we know from sketching derivative graphs that a corner in the original graph will correspond to a jump in the graph of its derivative. So when we see a jump in a derivative graph, we say, okay, I think there's going to be a corner in this image. And aside from that jump, this picture also has not just like positive and negative values, right? So we do care this is above the axis, below the axis. So we'll be increasing, decreasing. But these are perfectly constant values. So for example, this piece here, this is all at y = 1. So for every single one of these points, the derivative is exactly 1. That tells me a constant derivative value is a straight line. So what I'm going to graph over here to the left of 1 is a straight line where the slope of it is +1. I still don't know exactly where to draw it, right? I'm going to have a slope of 1, so it's roughly this tiltiness, but it could be up in the air, down below, it could go through the origin. We don't have enough information to know, but it just has to have a slope of 1. So I'm just going to throw in a random point to get started. Let's say 1, 2, I don't know. And then I want to draw a line with a slope of +1. Here and here, and so it'll be like that. And then I'm going to stop abruptly there, and the slope switches. And now we have a slope of -2. And if it's exactly derivative -2 for all of these points, that means straight line with a slope of -2. So right here, I'm going to go down 2 over 1, down 2 over 1 like that. So now the original graph has constant slope of 1, abrupt change, no derivative, constant slope of -2. And that's my derivative graph.